Hello there. Welcome to Chapter 9, Subnetting IP Networks. This chapter will cover the importance of routing for hosts on different subnets to communicate, a description of IP as a communication protocol used to identify a single device on a network, network segmentation, subnetting an IPv4 network, variable length subnet masking, designing and implementation of a hierarchical addressing scheme, and how IPv6 address assignments are implemented in a business network. In early network implementation, it was common for organizations to have all computers and other network devices connected to a single IP network. All devices in the organization were assigned an IP address with a matching network ID. This type of configuration is known as flat network design. In a small business with a limited number of devices, a flat network design is not problematic. But as the network grows, this type of configuration can create major issues. For example, on an Ethernet LAN, devices use broadcast to locate needed services and devices. A broadcast is sent to all hosts on an IP network. On a large network, this could create a significant amount of traffic, which would slow down the network operations. For reasons such as this, larger network must be segmented into small subnetworks, keeping them localized to smaller groups of devices and services. The process of segmenting a network by dividing it into multiple smaller network spaces is called subnetting. These subnetworks are called subnets. Subnetting creates multiple logical networks from a single address block or network address. Each subnet is treated as a separate network space. Devices on the same subnet use an address, subnet mask, and default gateway that correlates to the subnet that they are part of. Planning network subnets requires examination of both the needs of an organization network's usage and how the subnets will be structured. Also, two very important factors that will lead to the determination of which private address block is required are the number of subnets required and the maximum number of hosts needed per subnet. Remember that the private IP addresses ranges are 10.0.0.0 with a subnet max of 255.0.0.0 and 172.16.0.0 and 192.168.0.0 with a subnet mask of 255.255.0.0. Knowing your IP address requirements will determine the range or ranges of host addresses you implement. Subnetting the selected private IP address space will provide the host address to cover your network needs. IPv4 subnets are created by using one or more of the host bits as network bits. This is done by extending the mask to borrow some of the bits from the host portion of the address to create additional network bits. The more host bits borrowed, the more subnets can be defined. For each bit borrowed, the number of subnets available is doubled. For example, if one bit is borrowed, 2 subnets can be created. If 2 bits borrowed, 4 subnets are created. If 3 bits are borrowed, 8 subnets are created, and so on. However, with each bit borrowed, fewer host addresses are available per subnet. These are guidelines for each of the subnets. These are the guidelines for each of the subnets. The network address is the one with all 0 bits in the host portion of the address. Here, the blue one. The first host address is the one with all 0 bits plus a rightmost one in the host portion of the address. The last address is the one with all ones plus a rightmost 0, and the broadcast address is the one with all 1 bits in the host portion. This formula can be used to calculate the numbers of subnets and hosts. To calculate the number of subnets, take 2 to the power of n, where n is the number of bits borrowed. And to calculate the number of hosts, take 2 to the power of n and subtract 2, where n is the number of bits remaining in the host field. We subtract 2 here because we need to subtract the network address and the broadcast address. For example, here 1 bit is borrowed, so the number of hosts is 2 to the power of 1, which is 2. So there are 2 available subnets. And the number of hosts in each subnet is 2 to the power of the number of bits remaining in the host field, which is 7 here. So 2 to the power of 7 is 128. 128 minus 2 is 126. So there are 126 available hosts per subnet. This means that each of the subnets has 126 valid host addresses. Remember that bits can only be borrowed from the host portion of the address. The network portion of the address is allocated by the service provider and cannot be changed. Every network within an organization is designed to accommodate a finite number of hosts. Basic subnetting requires enough subnets to accommodate the network while also providing enough host addresses per subnet. Using traditional subnetting, the same number of addresses is allocated for each subnet. If all the subnets have the same requirements for the number of hosts, this fixed size address blocks would be efficient. Nevertheless, most often that is not the case. So applying a traditional subnetting scheme could be very inefficient and wasteful. So what we do is we subnet an already subnetted network. Subnetting a subnet or using a variable length subnet mask (VLSM) was designed to avoid wasting addresses. VLSM allows a network space to be divided in unequal parts. So with VLSM, the subnet mask will vary depending on how many bits have been borrowed for a particular subnet. Thus, the variable part of a VLSM. VLSM subnetting is similar to traditional subnetting in that bits are borrowed to create subnets. The formulas to calculate the number of hosts per subnet and the number of subnets created still apply. The difference is that subnetting is not a single pass activity. With VLSM, the network is first subnetted and then the subnets are subnetted again. And this process can be repeated multiple times to create subnets of various sizes. Some networks, such as point-to-point WAN links, require only 2 hosts, and other networks, such as a user LAN in a large building or department, may need to accommodate hundreds of hosts. So network administrators must devise the inter-network addressing scheme to accommodate the maximum number of hosts for each network. And they need to remember that the number of hosts in each division should allow for growth in the number of hosts.
So we will analyze quickly the considerations for address allocations on a network, not only on IPv4 but also on IPv6 networks. So first, 3 main considerations: preventing duplication of addresses, so each host can have a different addresses to avoid issues on the network; controlling the access and also providing access, because if we do not assign the addresses in a certain way, we cannot determine which devices can and cannot access to the network because we don't know their address. And also, we really need to know which addresses are who, because if we need to know security or we need to know performance, we would want to know where does the network is failing. And in a network tool, you won't know this if you don't know exactly how your addresses are allocated. So the addresses are assigned different for each device. We will cover this mainly. End user clients, servers and peripherals, hosts, intermediary devices, and gateways. We will give a really quick summary of each of them. So here's a quick sample that you can see to illustrate how the addresses were given in this particular example. So first of all, the end user clients are addresses that cannot be given manually or statically for laptops, computers, mobiles. You wouldn't want in a network to give your computer an address for each of all of the computers that are on the network. And if all the computers are connected at the same time, they will all have a different address. So for this sake, the DHCP, Dynamic Host Configuration Protocol, was created. This is important in two ways because, first of all, you are not responsible of assigning a certain address to an end user. This protocol solves it. And second, because the addresses are only leased while they are being used. So the time that passed while then the address is available really frees a lot of addresses within the network. Then we have the servers and the peripherals. Unlike the end user clients, these servers have to be static. They cannot be leased, or they cannot be dynamically predicted every time you enter the network. And although it can be done, we are talking of the ideal case. So servers like printers or any other device. First of all, every time you connect to a network, you would want to know where is your server, where is your printer. So you don't want your printer to be every time it connects to the network in a different address. You would always want it to be on the same address. So for this thing, this has to be static. Predictable, because if you are assigning more than one peripheral or a server, it would be easier for you to determine that if the one is the server 1, the 2, well, must be the server 2. That's a bit obvious. So if you have this organization in your addresses, it will be really easy to identify the set of servers and peripherals in your network. Like you can see an example, you have from 230 to 239 ranging in servers and peripherals. So also easy to identify. Like they are really big allocations of traffic. If you are monitoring your network and you know your servers are in this range, and you see a big allocation of traffic in one of these addresses, you know what is happening. Then we have the hosts that are accessible from internet. These are the most tricky ones. So first of all, there are not plenty of them on a network, but the main concern of these hosts are that they have a public space address association with a private space. So they have this public address, or this public address that has the internet access, but also has the communication to the private network. So for this communication to be successful, the gateway has to resolve the configuration. And if this configuration is not done in static and predictable addresses, this can really be a hassle. So for this specific thing, this has to be static and predictable on every host that is accessible from internet. Then we have the intermediary devices like switches. As well as servers, they are a concentration of a lot of traffic, so we also would want to use easy to identify addresses. We would want to use different range from the end user devices for them not to get all mixed up. That's a bit obvious. Also, these are static and manually assigned. And this is a bit like the thing of the servers. You would want to know that each switch has a sole only address and that they are assigned in a logical or predictable way. So you would know that switch 1 is address 1, just for saying an example, and that switch 2 is address 2. This is an easier way to set up your network to bring support to it later. So this is important for switches. Then the gateway. The gateway, it can be a router or firewall, has a particular difference with the servers and the switches. Although the gateway is a concentration of a lot of traffic, the gateway has an IP for each interface. So the special thing that is done here is that the router assumes or uses the lowest or highest address in the network. So no matter where you are, you know which is your gateway, which is the address of the router. And also, well, you have to have logical addressing because a router can have a lot of interfaces. So if you are not using logical addressing, you won't get your addresses properly easier when you're trying to solve problems or just trying to move things in the future. Well, IPv6 subnetting, it's a bit different from IPv4. In IPv4, we are trying to save as much addresses as we can, so we subnet as much as we can. And in IPv6, we have a lot of addresses. We can see this in this, well, we'll see later, but mainly we can have almost 65,000 addresses per subnet, which is a lot. So this subnetting requires a different approach. The primary reason is that here we are not trying to conserve addresses, and we are trying to form a logical hierarchical design. We are trying to use numbers to be logical in our design. So here, for example, that we have 1 1 and 2 LANs, we in our IPv4 we would conserve addresses by subnetting. Here we are not doing this. We're giving each part of the network a subnet with more than 65,000 available subnets. Here we have these subnets that are ranging from 0001 to 005, assigned equally to each of the subnets in the network, and we are giving them 65,000 available subnets. So that's more than they will ever use, but we are trying here to form a logic or a hierarchy to understand better our network. That's mainly the difference between IPv4 and IPv6. The other difference is that in IPv6 you can subnet into the interface ID, and this is not done, well, as a side effect you save addresses because you are subnetting, but this is not done to save addresses. This is done for security reasons, because you reduce the number of hosts, but also it gets really predictable for the subnets to know the interface ID, because you take the whole hexadecimal nibble, that it's how it's called, that it's an hexadecimal or a 4-bit, from the interface ID. So it's really easy to know what's this nibble of the interface ID. For example, here we have our 000, and we assign the extra 0 from the interface ID, and we can see how this happens till the FFF, that is the last example, with the F from the ID from the interface. So it's really easy for us to know the ID extended, and this makes it a lot easier for us to identify things. This is the best practice for subnetting into the interface ID, and it's really recommendable to do it. And well, lastly, as a quick summary, we have to remember that IPv4 subnets are created using one or more of the host's bits as network bits. Two very important factors that will lead to the determination of the IP address block with the subnet mask are the number of subnets required and the maximum number of hosts needed per subnet. The more bits borrowed to create subnets, the fewer host bits are available. Therefore, fewer hosts per subnet, which is a good thing. IPv6 subnetting requires a different approach, as we see. The IPv6 subnetting is about building an addressing hierarchy based on the number of routers and the networks they support. No matter which planning you're doing, IPv4 or IPv6 design, a careful planning of a network makes it really easier to support it and to give backup to the network. Every network's success and easiness in its monitor and the considerations we took at first are done by a good design and a good consideration on the address allocation.